Quantitative chemical analysis, it relates to the determination of the amount or concentration of a substance in a sample. And simply put, this means it is a method by which we figure out how much of something we have in a sample. It can be done typically using two types of analysis techniques. Titration is the one where we combine two solutions, and in this case we ideally find the concentration of a solution in a sample, or if we react a certain amount of solid, as will be the case for the standardization of the sodium hydroxide solution with KHP. In that case, we know the amount of KHP going in, and then we figure out how much of the sodium hydroxide solution we use. In the case of gravimetric analysis, typically the outcome of the chemical analysis is the production of some kind of solid, and in that case it's going to be, once you collect the solid, you determine its mass. From the mass you determine the moles, and then from there you find out where that material originated from, and you can do those calculations quite easily. That will be the topic of our next slideshow on gravimetric analysis. In this sequence, let's focus on the titration, and I would like to start with this because this week we are going to address our acid-base titration experiment, and next week we're going to address the redox titration experiment. So this is doubly important, and that is the reason why I moved this topic ahead in chapter 7. Titrant is what we put up top here. This vessel is called a burette, and the analyte, the one that we're trying to use to determine the concentration of the titrant, is going to go in this vessel that we call the Erlenmeyer flask. Every time when you have two solutions that are colorless, so here, while it's not shown, this is more likely a base that is colorless, and on the bottom you have an acid that is colorless. And so when two colorless solutions mixed, often the outcome is going to be another colorless solution, which then does not give you a visual way of determining whether you were successful or not in completing the reaction. So for acid-base titration, what causes this color here is an acid-base indicator called phenolphthalein. Of course, you could use other indicators, but the most common one in chemistry labs will be phenolphthalein. When the color changes in the Erlenmeyer flask that contained the acid and the indicator at first, because enough base was added, that's what we call the endpoint. Now the endpoint will greatly depend on the type of indicator that is used, because some indicators are going to change their color in the acidic range, some in the basic range. Phenolphthalein specifically changes its color at about a pH of 8. So it's going to be slightly basic, which means there is a little bit more base here than is necessary to consume all the acid that was originally added in the Erlenmeyer flask. In this titration problem, we have hydrochloric acid reacting with sodium hydroxide. Hydrochloric acid is an acid because it starts with hydrogen, and sodium hydroxide is a base because it contains hydroxide. Now I like to pull out the information first. The volume of hydrochloric acid is known. It is 50.00 milliliters, which says it was recorded with fairly accurate equipment. The volume of the sodium hydroxide in this case is 35.23 milliliters, and the fact that there are two significant figures makes me think that this was done with a burette, and whoever completed the experiment recorded the volume correctly. We also know the concentration or the molarity of the sodium hydroxide, and that is 0.250 moles per liter. And I like to keep this instead of molar because it gives me the two units that are connected through that conversion factor. So let's look at how these calculations are done. The first thing I like to do is convert my milliliters into liters by dividing them by 1,000. So this is 0.03523 liters, and this is 0.05000 liters. So step 1, go to moles. And when we have volume and concentration, the way we get to moles is by taking the volume in liters. So 0.03523 liters. And this is of the sodium hydroxide solution. And then we're going to say in every 1 liter of the sodium hydroxide solution, we have 0.250 moles of sodium hydroxide. And with that, we are at moles of sodium hydroxide, and now we can use the stoichiometric coefficients in the chemical equation to convert from moles of sodium hydroxide to moles of hydrochloric acid. In front of sodium hydroxide, we have an assumed 1. In front of hydrochloric acid, we have an assumed 1. So now we are at moles of hydrochloric acid, and this is a good place where we should and can stop the chemical, our sequence of reactions. So if we do this calculation, then we're going to have 0.00808 moles of hydrochloric acid. And if we have the moles of hydrochloric acid and we have the volume that they come from, then we can calculate the molarity of hydrochloric acid, which is simply moles of hydrochloric acid divided by the volume of the solution, which in this case, expressed in liters, is going to be this many. And as we complete our calculation, we find that the answer is 0.176 moles per liter. All right. Now that you've seen the solution, the other thing I want to point out that is really important, keep track of what belongs where. The volume of the hydrochloric acid has to always accompany either the moles of hydrochloric acid or the concentration of hydrochloric acid. And the same thing goes for sodium hydroxide. You can only calculate moles if you're using the volume and the concentration of the same solute. This problem is another example of a titration because we are provided with the volume of two solutions. So if we're combining two solutions, that automatically makes it a titration reaction. So let's extract the information first. The volume of hydrochloric acid is 43.8 milliliters. And in step 1, let's automatically convert it to liters. We also know the volume of the barium hydroxide solution, which is 37.6 milliliters, which converted to liters is 0.0376 liters. The concentration of the hydrochloric acid solution as provided is 0.107 moles per liter. And the question is, what is the concentration of the base? So concentration of barium hydroxide is unknown. Now, in order to have concentration, we need moles of barium hydroxide and we need the volume of the barium hydroxide solution. We already know the volume of the solution. Now we need to find out the moles. We can't find out the moles of barium hydroxide directly from the volume and the concentration, but we can find out the moles of hydrochloric acid from its volume and concentration, and then we can relate it 2:1 hydrochloric acid to barium hydroxide. So let's do that. We'll start with the volume of hydrochloric acid solution, and then we're going to say that in every 1 liter of the hydrochloric acid solution we have 0.107 moles of hydrochloric acid. Then we're going to say that in order to react hydrochloric acid with barium hydroxide, for every 2 moles of hydrochloric acid, we also need 1 mole of barium hydroxide. And with that, everything but the moles of barium hydroxide cancel out. And we're going to get a number for this, and that number is going to be 0.0438 multiplied by 0.107 and divided by 2, and we have a fairly small number, 0.00234 moles of barium hydroxide. And then we're going to say that the molarity of the barium hydroxide solution is the number of moles, and let me put this a little further back, 0.00234 moles of barium hydroxide, and all these moles are in the 37.6 liters of solution. And so the final number here is going to be 0.0623 moles per liter of the barium hydroxide solution. This is another titration problem because we're looking at 2 solutions being combined. It is also an acid-based titration because we're having perchloric acid and barium hydroxide combined together. Now, if we extract the information, we have the volume of the barium hydroxide solution as 28.6 milliliters, and of course we convert this automatically to liters so that we don't get confused about the necessary units. The molarity of barium hydroxide is also provided, and that is 0.176 moles per liter. The concentration or molarity of the perchloric acid solution is given, and that is the 0.399 moles per liter. Because remember, molar stands for moles per liter. And then unsurprisingly, the question is asking for volume of perchloric acid. So the first thing that we can and should do is to calculate from volume and concentration of barium hydroxide the moles of barium hydroxide. From moles of barium hydroxide, we can then calculate the moles of perchloric acid, and then from moles and concentration, we can determine the volume. Let's do that. We begin with the volume of the barium hydroxide solution. And then we're going to say that for every 1 liter of our barium hydroxide solution, we're going to have 0.176 moles of barium hydroxide. And now that we are at moles of barium hydroxide, we need to find the moles of perchloric acid. So from moles of barium hydroxide, we'll convert to moles perchloric acid. In front of the barium hydroxide, we have a 1. In front of the perchloric acid, we have a 2. So if we do this calculation, we're going to have the moles of perchloric acid. And that number is going to be 0.0286 times 0.176 times 2, and that gives us 0.01007 moles of perchloric acid. Now that we have the moles, we're going to say that 0.01007 moles of perchloric acid are going to be in the following volume of solution. So in every 1 liter of the perchloric acid solution, we have 0.399 moles of the perchloric acid. And notice the moles cancel out, and at the end we're going to have liters of the perchloric acid solution, which then can be converted into milliliters by simply multiplying it by 1,000. And here the answer is 0.0252 liters, which converted to milliliters is 25.2 milliliters, and that makes the correct answer option D.